Look at this. This is a slag heap. You've probably seen one without knowing what it was. A massive pile of waste rock left behind after a mining operation extracts what it needs and discards the rest. Irregular, broken, hollowed out in places. The remains of something that was systematically processed and stripped. Now look at this. This is a mountain range. Tell me the difference. Not the size. Forget the size for a moment. Look at the shape. Look at the hollows. Look at the way the material seems to have been removed from certain sections while other sections remain intact. Look at the way entire faces of these formations are missing, not eroded, not gradually worn away by wind and water, but absent, as if extracted. You can't tell me the difference, because visually, structurally, geometrically, there isn't one. And here is the question that mainstream geology will not answer. If the giant trees existed, if the flat-topped formations we've been calling mountains are their mineralized stumps, then what happened to the material above the stump line? Where did the trunks go? Hundreds of meters, kilometers, of biological material, silicon-rich, carbon-rich, dense with minerals accumulated over hundreds of thousands of years of growth. You don't just lose that material. You don't just wave it away with an erosion explanation. Either it burned or it was processed. And the evidence, sitting in plain sight across every mountain range on Earth, suggests that both happened. And that the processing happened on a scale that makes every mine in human history look like a hole in a backyard. Stay with me, because what you're about to see is going to reframe everything you think you know about where our metals come from, where our coal comes from, where our oil comes from, and who or what did the extraction. Part 1. The material problem. Let's start with something that mainstream science agrees on completely. The Earth's crust is extraordinarily rich in specific materials: metals, carbon compounds, silicon, rare earth elements. These materials exist in concentrations that, by the standard models of planetary formation, should not be where they are. Gold, for instance. The standard model of planetary formation holds that, when the Earth was molten during its early formation, virtually all of the heavy metals, including gold, should have sunk to the core. The density of gold is nearly 20 times that of water. In a molten planet, it goes down, fast, deep, far beyond any depth we could ever mine. And yet gold exists in the crust, in concentrations that have supported human mining for thousands of years, in veins and deposits that sit at depths we can reach. The official explanation is something called the late veneer hypothesis, the idea that after the Earth's crust solidified, a period of heavy asteroid bombardment delivered additional metal-rich material to the surface. It's a reasonable hypothesis. It might even be partially correct, but it doesn't fully explain the distribution. It doesn't explain why the richest mineral deposits on Earth are found in specific geological formations. Formations that, when you look at their structure, look less like asteroid impact sites and more like the remains of something that accumulated minerals over a very long biological lifetime. Trees accumulate minerals. Every biology student knows this. A tree draws minerals from the soil through its root system and incorporates them into its structure over its lifetime. A small tree in a typical forest accumulates measurable quantities of calcium, potassium, magnesium, iron. Now scale that process up. A tree that stands for 100,000 years. A tree with a root system extending kilometers in every direction. A tree with a trunk diameter of 300 meters drawing minerals from deep geological layers, far beyond the reach of any modern tree's roots. What would that tree contain when it died? And what would be left in the ground where it stood after that material was extracted? The answer, when you look at where the world's richest mineral deposits actually are, is uncomfortable. They are exactly where the stumps are. Part 2. Coal and the carbon question. Let's talk about coal. The official explanation for coal is this. Hundreds of millions of years ago, Vast forests of primitive plants died, accumulated in swampy lowlands, were buried under sediment, and over millions of years of heat and pressure were transformed into the carbon-rich material we burn for energy today. It's called the biogenic theory of coal formation. It is taught in every geology class on Earth. It is the foundation of the entire fossil fuel industry's self-understanding. And it has a problem. Several problems, actually. The first problem is the quantity. The coal deposits of the Earth represent an almost incomprehensible quantity of biological material. The total estimated coal reserves, just the known, mapped, economically accessible deposits, represent billions of tons of compressed carbon. The amount of plant material required to produce that quantity of coal, under the compression ratios that geology acknowledges, would require forests of a scale and density that the Earth's current biology cannot support, and that the geological record does not clearly document. Where did all that biological material come from? The second problem is the distribution. Coal deposits exist on every continent. In Antarctica. In regions that, under the current understanding of ancient climate and geography, should never have supported the kind of dense swamp forest that coal formation requires. The official explanation involves continental drift, the idea that the coal-forming regions were once located in more tropical latitudes. This explanation works for some deposits. It doesn't work for all of them. The third problem is the formation time. The Standard Model says coal formation takes tens of millions of years, but there is a growing body of research suggesting that under the right conditions, specifically the conditions that would exist in the aftermath of a catastrophic global event involving the burning and burial of enormous quantities of biological material, coal can form in thousands of years, possibly hundreds. Now put those three problems together and ask a different question. What if the coal is not the compressed remains of small ancient plants? What if the coal is the compressed, carbonized remains of the giant trees? The scale is right. Silicon-rich biological material, subjected to catastrophic burning and burial under the debris of a global impact event, compressed by the weight of everything that fell on top of it in the aftermath. The distribution is right. If the trees existed on every continent, which the stump evidence suggests they did, then the coal would exist on every continent too. The formation time is right. 12,000 years is not long in geological terms, but it is long enough, under catastrophic compression conditions, to produce coal. And here's the detail that makes this impossible to dismiss. Coal seams frequently contain something called fossil tree trunks. Vertical tree trunks, sometimes meters in diameter, standing upright through multiple coal seam layers. These are called polystrate fossils. Fossils that cross multiple strata, defying the assumption that each layer represents millions of years of slow deposition. The official explanation for polystrate fossils is tortured. It requires coal layers that were supposedly deposited over millions of years to have somehow preserved a standing tree trunk without decomposing it. The alternative explanation is simple. The tree was there first. The coal formed around it, quickly, because the coal is the tree. Part 3. Oil and the deeper question. If coal is the compressed carbon remains of the giant trees, then what is oil? The official theory of oil formation, the biogenic theory, is even more difficult to defend than the coal theory. Oil is supposed to be the remains of ancient marine organisms, primarily algae and zooplankton, that died and accumulated on ancient seafloors and were then buried and subjected to heat and pressure over millions of years. The problems with this theory have been documented by mainstream petroleum geologists for decades. The quantities required are staggering. The distribution doesn't match ancient marine geography in the way the theory predicts, and perhaps most damningly, oil is consistently being discovered at depths that the biogenic theory cannot account for. Depths where no organic material should ever have reached. This has led a significant minority of geologists, particularly in Russia and Ukraine where the competing theory was developed, to argue for what's called the abiogenic theory of oil formation, the idea that oil is not biological in origin at all, but is produced by deep geological processes involving carbon compounds in the Earth's mantle. But there is a third possibility that neither the biogenic nor the abiogenic theorists have seriously considered. What if oil is the processed liquid byproduct of the giant tree material? Silicon-rich biological material subjected to catastrophic heat, pressure, and transformation in the aftermath of a global impact event would produce a complex mixture of carbon compounds. Some of those compounds would become coal. Some would become the complex hydrocarbon mixtures we call oil and natural gas. The deepest oil deposits, the ones that the biogenic theory can't explain because they're too deep for organic material to have reached, would be explained naturally. Because the roots of trees that stood kilometers tall would have extended to extraordinary depths. Their root material, subjected to the same transformation process, would have produced hydrocarbon deposits at depths that have nothing to do with ancient seafloors. And here's the fact that should stop every petroleum geologist cold. Oil fields and coal deposits are systematically co-located with the geological formations we've been calling mountains. The richest oil deposits in the world sit beneath mountain ranges. The Zagros Mountains of Iran and Iraq, the Andes of South America, the Carpathians of Eastern Europe, the formations of the Arabian Peninsula, stumps, every one of them. And beneath the stumps, the processed remains of what the stumps used to be. Part 4. The mining evidence. Now we arrive at the part that turns this from a geological theory into something more disturbing. Because if the giant trees contained extraordinary concentrations of minerals accumulated over hundreds of thousands of years, and if their processed remains became the coal and oil deposits that sit beneath the stump formations, then someone, at some point, would have had very strong reasons to extract those materials. Look at the mountains. Not at the famous mountains. Not at Everest or the Alps or the Rockies in their photogenic entirety. Look at the mining mountains, the mountains that humans have been digging into since the earliest recorded history. The copper mountains of Cyprus, whose very name comes from the Latin for copper, so thoroughly identified with metal extraction that the island and the metal share an etymology. The iron mountains of the Atlas Range in North Africa, mined since before recorded history, their ore deposits sitting in formations that show the same columnar geometry as every other stump structure on Earth. The gold-bearing formations of the Witwatersrand in South Africa, the richest gold deposit ever discovered on Earth, sitting inside a geological formation that mainstream science calls an ancient meteor impact crater, but whose structure, when you look at it carefully, looks far more like the base of something that was once biological. The coal mountains of Pennsylvania and Wales and the Donbass, where miners in the 18th and 19th centuries drove tunnels into seams and found, with consistent regularity, the upright remains of enormous trees embedded in the coal they were extracting. The trees were in the coal. The coal was in the mountains. The mountains were the stumps. And the humans who found all of this, who built entire civilizations on the energy and metals they extracted, never asked why the richest deposits on Earth were concentrated in specific formations, never asked why those formations had a geometry that didn't quite fit the geological models, never asked why the cultures who had lived among those formations for thousands of years before the miners arrived described them not as mountains, but as the remains of something that was once alive. They just dug,